Routing within IP works differently if the information is being distributed within an autonomous system versus being sent between different systems. Within the same autonomous system, one uses a class of routing protocols known as Interior Gateway Protocols, or IGP. RIP and OSPF are examples of these kinds of protocols. Between autonomous systems, one uses a class of protocols known as Exterior Gateway Protocols, or EGP. The major reason for the division of duties between these protocols is to protect the backbone nodes from bad routing information. Suppose for a moment that Network Yellow advertised to the backbone a path to Site Blue. Unfortunately, Site Blue is connected to Network Blue, so if traffic for Site Blue is forwarded to Network Yellow, the traffic will never arrive at its destination. The other reason for the IGP-EGP split is the hiding of routes. Suppose you run a network on which you have highly sensitive company data, such as payroll records. By placing the machines that need to exchange information about your payroll in a separate network, and then not advertising that network outside of your network or autonomous system, no one will be able to access your payroll information. One example of external gateway protocol is the Border Gateway Protocol, or BGP, which is specifically designed to spread information about networks between autonomous systems. BGP enables the autonomous systems to set a policy on the kind of addresses advertised within and between networks. BGP has a list of the autonomous systems that a packet will have to traverse in its path from source to destination. This AS path can be used to filter advertisements, such as, "I don't want routing information about this AS," or "I can't send my commercial traffic across this AS." These features of BGP are the first steps toward policy-based routing, or routing traffic according to a series of policy statements. Border Gateway Protocol is a TCP-based incremental updating protocol. BGP will send an update as soon as it knows about the new network. TCP always guarantees reliable delivery, or notification that a delivery was not made. This way, an autonomous system always knows what routing information is being advertised to remote networks. The Transmission Control Protocol, known as TCP, is used to move data between hosts which are connected to IP networks. TCP makes no differentiation between hosts which are sitting several feet apart or hosts that are thousands of miles apart. TCP makes guarantees about the data arriving at the remote host and arriving correctly. In those instances that data packets must be split into pieces and sent across an unreliable packet network, TCP guarantees no data corruption, and data will arrive and be reassembled in the correct order. In order to guarantee delivery, TCP uses many things such as sequence numbers, checksums, and timeouts to ensure the data is delivered across the network correctly. To explain the very basic process of the Transfer Control Protocol, it would look something like this. Each packet of sent data, once received by the destination, has an acknowledgement sent back to the source. This method of transfer can be quite slow, especially if that packet has to traverse a satellite. Each time the data packet is sent via satellite, it takes 4 seconds each way to go from the local host up to the satellite and back down to Earth to the remote host. So in total, it would take 8 seconds just to send 1,000 bytes of data to the remote host and have an acknowledgement that the packet is received. One way to improve the transfer rate is to have more data in transit by sending more data at the same time. To speed up TCP's guaranteed deliver process, a mechanism called sliding windows was created to ensure that the maximum amount of data is always in transit within the data network. Let's say our transmission window size is 3K and each data packet is 1K. So the window can hold 3 packets, enable, and the first 3 hunks of the file can be sent at the same time, but in sequence. Once the first packet is received, an acknowledgement is sent. The window then slides to the right to incorporate the 4th packet, which then is sent. Packet 2 is received and acknowledged, and packet 5 is then sent, and on and on. TCP ports is a mechanism within TCP that enables it to keep track of what application is being used on the source and remote computers. For example, on the same computer, the file transfer protocol and the remote login processes will use TCP. TCP, in turn, needs a way to send the file to the file transfer process and the login data to the remote login process. The way that TCP keeps data flowing between applications correctly is to use ports. On the source and remote machine, TCP assigns a number to uniquely identify the application to which the data should be sent. This number is called the preassigned port number. So if you want to connect to Telnet, fill in the destination port number 23.